Welcome to the introductory screencast for GPI, the Graphical Programming Interface. I'm Nick Zwart, and I'll be giving a quick overview of what GPI is and what it is used for. GPI is a graphical development environment for scientific algorithms. GPI is a modular framework. The screenshot on the right shows the GPI canvas, and on the canvas are nodes connected to create a flow diagram. The nodes represent algorithm elements. As you develop an algorithm in GPI, you'll tend to reuse existing nodes as opposed to rewriting them, which further enforces modularity and is one of the benefits of modularity. The modular design and graphical interface make it easy to perform unit testing, test-driven development, data, and algorithm analysis as a natural side effect. You can generate algorithms on the fly with existing nodes, and some nodes allow you to program code directly in their widget interface, allowing you to make small adjustments without having to create a new node. The code interfaces are easily abstractable if a few guidelines are followed while coding your algorithm. This allows you to write Python or C++ code in GPI and then share it with others who are not using GPI. This is an important concept when talking about prototyping code for a different system, such as the Philips Reconstruction platform. GPI is written in Python, which is a multi-platform language. Currently, we have native installer packages for OS X and Linux. We use GPI here at the Keller Center mostly for MR data reconstruction, but there is nothing about the GPI framework that is specific to reconstruction. We also use it for spin simulations, MR data simulations, and even some initial pulse sequence development where we want to analyze gradient or RF waveforms for custom case-based trajectories. These are also portable algorithms that are used in the pulse sequence side without code modification. This is some of the vocabulary we use to describe the elements of the graphical interface. You can see that there are nodes on the canvas which are connected by edges and ports. Some of the nodes contain multiple in ports and out ports. The nodes are instantiated on the canvas by selecting them from the Node Library menu, which is a right-click menu on the canvas here. Right-clicking on any node will raise its node menu as shown on the left. The node menu contains widgets for visualizing data or parameterizing algorithms. You can see that there is a display widget showing an axial T2 scan, and below that there are sliders and numbered boxes allowing the user to adjust the image scale and a push button allowing the scale to be reset. There's also an About widget at the bottom, which displays the node usage documentation generated from the comments made in the code. There are two code interfaces that are designed to make programming in GPI as simple as possible. The node description is a pure Python code that describes the widgets and ports for each node. Adding a new widget or port requires only one line of code. The GPI menu layout is fixed and yet highly extendable, allowing you to focus on your algorithm instead of dealing with UI calls. The other piece of the node description is the implementation of the compute function. This is where your algorithm will tie into the node, getting data from widgets and ports, processing with your algorithm, and then passing new data to downstream nodes, which are all one function call apiece. GPI is packaged with a C++ interface that we are also developing in-house called PyPhi. PyPhi is a bridge between Python and C++ that makes it easy to extend Python, which is the usual case where you want to call C++ routines from Python, or embed Python, which allows you to call Python functions from C++. PyPhi also provides an array object similar to the NumPy Python array that contains all the information necessary to parameterize a multidimensional array of various base data types. This array object acts as the C++ counterpart to the NumPy arrays. Nodes embody modularity and portability. Node development is the gateway to providing new algorithmic functionality to GPI. The GPI framework itself relies on a few third-party packages with the goal being to make it easier to maintain. Nodes can implement any necessary third-party package, and if that package is deprecated, the loss is minimized to that node. Another advantage of the node interface is widgets and ports. When an algorithm is implemented in a GPI node, it provides an easy means for the end user to start using that functionality because the widgets and ports belong to a common user interface. This also opens the algorithm up to being used for purposes that potentially fall outside the original intended use. As long as the port data constraints are satisfied, the node will execute. Now let's look at some examples. This is a screen capture of a spin simulation network that numerically solves the block equation for a spin system with modifiable attributes which are set in the spin node. The block node defines the gradient and RF fields over a specified duration. Simulation sequences can be built up by daisy chaining the block nodes. There are a few output options shown, starting from the left. The magnetization profile for a given time frame can be plotted. The middle display shows a plot of the sequence. In this case, an asymmetric RF pulse is being paired with a slice select gradient. The display on the right shows a 3D GL rendering of the spin system. The movie is made by building up all of the frames corresponding to each time point in the simulation. This example highlights the use of modularity and generalized algorithms. This k-space filter is made from basic, generic components such as the FFT node, a math node, a shapes node, and a couple of other nodes. The shapes node is one of those workhorse nodes that often finds its way onto the canvas. It simply defines a window function for a 1, 2, or 3D array, but this can be used to create filters, masks, and even generate trajectory coordinates. The menu to the right shows a list of implemented functions: ellipse, rectangle, Hanning, and so on. All the usual suspects in MR data processing. In this case, the shapes node is generating a 2D filter which is being displayed in the viewer to the bottom left. The display shows a color scale black to white indicating values ranging from 0 to 1. In the case of a filter, the stop band will be 0 and the pass band will be 1. The viewer shows two lines dividing the filter image. These lines are cross-sections taken out of the image for plotting in the above display. You can see that as the Shapes menu is modified, the canvas immediately works to resolve the changes with the rest of the node network by executing all node compute functions that are affected by the change. The node compute is signified by changing its color to a dark gray. Finally, the image on the upper right shows the original and high-pass filtered image in the same display window. The reduce node makes it easy to take cross-sections of data at any position within the array. This is really just a subset of the reduce node's capability, which can be thought of as making rectangular masks of any dimensionality within a multidimensional array. This example shows how a slicing slider on the second dimension changes the vertical position of the cross-section. The sliders above are set to crop using a center width convention where the mask is centered on point 227 and the mask width is 200 points. The 3D GL viewer can also be used to visualize k-space trajectories. Here, spiral k-space coordinates are generated and then passed to a GL object node, which creates a list of cylinders to represent the trajectory, and then appends an axis and a clipping plane before passing to the GL viewer. The top two images are rendered trajectories of a spherically distributed spiral set and floret spiral hub. The bottom two are the same trajectories with a clipping plane added to show the sample distribution within the 2D cross-section. Well, that's all for now. You can find more information by visiting gpilab.com.